Okay, so that's the 4 topics for today. The TAs did ask me also to say something about the appropriate use of TA time because they are being somewhat overwhelmed right now, and there's just a few things that I wanted to say as to kind of expectations with the TA hours. So the first thing is that if you have questions outside of TA hours, please post to Piazza. So outside TA hours, please post to Piazza. I know that some of you have TAs you like, and you like to email them or get with them with certain other applications, but they have their own work to do, their own activities, and they don't necessarily have time to respond to emails. So that's why we prefer you post to Piazza, because everyone, all TAs and I, have a chance to look at it there. So rather than emailing the TAs, I've told them you're not responsible to respond to email about questions with code outside of office hours. It's just they have their own. 3 of them are undergraduate TAs, and they need to get their own work done. They have a pretty heavy load. The second thing is the TAs are there for conceptual help and to help with debugging, not to give you code. So it's the TAs feel that sometimes all some of you are looking for is code, and that's just not appropriate. You've got to learn how to write the code yourself. They can provide you conceptual help with understanding the lab problem or a high-level approach for attacking it, but they're not there to give you code. And with debugging, it takes a long time to debug your programs at this point. It even takes me, who's an experienced debugger, often half an hour if all I'm given is a program and a grade script. You have to learn to do some of this debugging before you come to lab. There is a technique. I thought it was called ring fencing. That's not it. I looked it up. But at any rate, using print statements, you try to basically herd the bug into a portion of your code. What you're trying to do with print statements is put a kind of, the bug might be here in your program conceptually, and with print statements you're trying to narrow down where that bug can be in the program so that you can narrow it down to a smaller piece of code. When you just come in with 100 lines of code and a grade script, first of all, those grade scripts are 800 lines. It's not, you can't just run the grade script. You have to narrow that grade script down to a few lines. So that's one thing you can do to help the TA, is eliminate a lot of the lines that are in a grade script and just get it down to a few lines. And oftentimes you would find your bug just as easily with a small example. So using small examples before you use the grade scripts, but also you need to use this technique of use print statements to narrow down, or to use print statements to put a fence around a bug. Okay, I'm seeing a lot of Piazza posts where students will say, I'm just not, it's sake faulting, I don't know why. And I think, well, use print statements to print out the contents, for example, of your bit matrices, and do that a lot, and you will see where things are going astray, because Dr. Plank gives you very detailed step-by-step accounts of how to solve specific examples. And if you run your programs with his specific examples and put print statements in there, you can figure out where your code starts to diverge from the correct answer, and that's going to make it a lot easier to figure out where the bug actually is. Now, sometimes when you have narrowed it down to a specific piece of code, it's still hard to find where the bug is, and that's where TAs come in very handy. But I've told the TAs, if you come in with a debugging problem, it's quite appropriate to say, what have you done on it so far? What print statements have you put in? What do you know about it? To just say, I have no idea where that bug is, that's not good at this point in the class. We're halfway through the semester. If you can't put print statements into your program and do a reasonable job of figuring out an approximate location where the bug is, you're probably not in a position to pass this course or succeed in 302. Okay? So at this point in the course, it's really not appropriate to tell a TA, I have no idea how to debug this program. You do. You can put print statements in and see what is being printed out. And you can see where it's still working and where it's diverging from what you expect the output to be. And it's also really not appropriate at this point to not be able to figure out what the output should be. In many cases, I know for the inverse function that was tough. Later in the course, we have a thing called the Shapeshifter Lab. But in general, you should be able to figure out what the expected output is for a problem. Okay? So just trying to help out the TAs there. I know it may sound a little harsh. I'm not trying to sound harsh. I'm just trying to help the TAs, okay, because they're feeling a little overwhelmed. And I understand why, especially Lab 5 was a difficult lab. Okay, I understand that. It's not, I don't think Lab 5 as a whole is difficult. I think the inverse function was difficult. Okay. I also want to say a few things about the Kino Lab, which is the current lab, because it involves using something called binomial coefficients, which you may not have had experience with. And I don't expect you to completely understand what a binomial coefficient is. If you haven't read the lab yet, Keno is essentially like the lottery. You pick, there's some number of balls. In Dr. Planck's example, there's 80 balls. And some number are picked. Maybe 20 balls are picked. And you have to get some number of balls correct, C balls correct, which is called the catch. Okay, in Powerball, I believe there's something like, I'm not exactly sure, 70 balls. I think they pick 6, and you have to get all 6 correct. Or 5, I don't know what exactly it is. But Powerball is essentially Keno. And what he's doing is having you do a couple things. First, figure out the probability that you get C balls correct, given that there's X number of balls and that Y balls are picked. And then the second thing he's asking you to do is calculate the expected value of your pick. And he has given you the formula for expected value. The thing that you have to do to calculate probabilities is you have to calculate these so-called binomial coefficients. So if you haven't seen them before, they're often written something like this. Okay, with big parentheses with one number on top and one number on the bottom. And what it essentially is saying is how many ways are there to select 2 balls from 4 balls. In general, the idea is if I give you X, Y, it's how many ways are there to select Y balls from X balls. So if we just think about numbering the balls, 1, 2, 3, 4, well, one way to select 4 balls is to select the balls 1 and 2. Another way is to select the balls 1 and 3. Another way is to select the balls 1 and 4. Then 2 and 3, 2 and 4, and 3 and 4. There turns out to be 6 ways you can select 2 balls from 4 balls. Okay, so there's a formula that can be employed. But first of all, let me give you some intuition. Okay? If you're selecting 2 balls, then the first time, how many choices do you have for the first ball? 4. You can select any of the 4 balls. The second time, how many balls are left when you select? 3. So the second time, you only have a choice among 3 balls. So there are actually 12 different ways that you can choose the balls. 4 ways for the first choice and 3 ways for the second choice. Okay, so that comes to 12, and I just showed you 6. Does anyone know why? So there's 12 ways to choose the balls, yet I said there's only 6 unique combinations. Because order doesn't matter. But here order does. So 4 ways I can select 1 or 2 or 3 or 4, and then I could select 2, 3, or 4. Here I could select 1, 2, or 1, 3, or 4. Here with the second ball I could choose 1, 2, or 4. And here I could choose 1, 2, or 3. But you'll notice that some of those are repeats. 1 and 2 is the same as 2 and 1. 1 and 3 is the same as 3 and 1. So there's repetition. So in fact, while there are 4 times 3 ways to choose the ball, there is also then, you have to divide that, each of the combinations like 1, 2, or 2, 1, those aren't unique. So it turns out that on the bottom, the number of times you can have the same combination is equal to what we call n factorial. In this case, it's 1 times 2. If I was choosing 3 balls, if I chose 3 balls, there are 3 factorial, or 1 times 2 times 3, 6 different ways you can order the same 3 balls. So if I have 1, 2, 3, I can also write it as 1, 3, 2. I can also write it as 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. There's 6 different ways I can write that. So basically, again, the idea is if I have 3 numbers, I have 3 choices for the way I can put the first number, okay, which is 1, 2, or 3. Once I've selected the first number, I have 2 ways to select the second number. Okay, here 2 or 3. With 2, it's 1 or 3. With 3, it's 1 or 2. And then with the third number, I have only 1 choice. So given any 3 numbers, I have 3 factorial ways of different ways of choosing those same numbers. So when I ask what is n choose k ways of choosing balls, it's really, let me go to a different page now. So n choose k, it's really n times n minus 1 up to n minus k plus 1 is the ways that I can choose k balls. And then that's over k factorial, because for any k balls, there are k factorial different ways of arranging them. So that's the formula. It just so happens that this formula, the numerator, can be rewritten as let me actually, as n factorial it's not completely right. Let me get the, actually, even I have difficulty coming up with the formula off the top of my head, so I'm going to look at the notes. Now let's get the formula, come on.
It's n factorial over k factorial times n minus k factorial.
Okay. I was right. It just didn't seem like, is that really right?
So the n minus k goes on the bottom.
Yeah, okay, thank you. That's what I was struggling with. I knew there was an n minus k. I couldn't, thank you. Okay. So it's n over k factorial, n minus k factorial. Okay, so that's, this is really n factorial over n minus k factorial divided by k factorial. So this and this numerator right here are the same thing. Dividing n factorial by n minus k factorial takes out all but these terms right there. So that's how he's coming up with this formula for n choose k. And now he's asking you to essentially calculate this because this is what you, the fundamental thing of the number of different ways you can choose k balls from n balls. Okay? And I'm not going to go into the full thing about now calculating probabilities. You can read that in the lab. But the important thing to realize is that n factorial, k factorial are very big numbers. They overflow memory very quickly. Okay, on my Macintosh, it overflows at 16 factorial. So you can't just do the easy thing. If you have 80 choose 20, you can't just calculate the product of 80 factorial. You'll get overflow. So what you have to do is what you did with fractions is you have to do cancellation. Okay, so for example, if you do have, let's make it a little bigger, let's say you had 6 choose 4, which is equal to 6 factorial over 4 factorial 2 factorial. That can be written as 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1, and then 2 times 1. And now you can do cancellation. So this 4 and this 4 cancel. Okay, this 3 and this 3 cancel. This 2 and this 2 cancel, giving us essentially 6 times 5 times 1 over 2 times 1 times 1. Of course, the 1s are unimportant. And now you can calculate this as 15. Now I will warn you, even after you do cancellation, when you're dealing with big numbers, you still can't just multiply out the numerator. You will still get overflow. So what you really are going to have to do when you're calculating your eventual products is you're probably going to have to actually calculate it as 6 divided by 2 times 5 divided by 1. You can't just go multiplying out the numerator, then multiply out the denominator, and then divide the numerator by the denominator. Instead, you're going to have to do it piecewise. Divide 6 by 2 to get 3, then divide 5 by 1 to get 5. Okay? Otherwise, you're still going to get overflow. And the way he's having you keep these numbers, these products, is in vectors. So you keep track of the terms in a vector. So in this case, in the numerator, there was, if you were keeping track in a vector, there was 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. That was the numerator. And then the denominator, which I'll just abbreviate as denom, it didn't go up as high, it only went up to 4. It had 2 1s, because there's 2 1s. It had 2 2s, so there's 2 2s, a 3, and a 4. So he's having you keep track of these products in vectors. So you have one of your functions is multiply number, or I think it's called multiply number. So if I multiply the numerator by 4, if I was to multiply the numerator by 4, I would increment 4, the index 4, to have the value 2. So it now has the value 2 because there's now a 2. There's 2 4s in the product. Okay, if I say multiply factorial, say 3, that's really saying multiply. Let's say I'm multiplying the denominator now by 3 factorial. That's saying multiply the denominator times 3 factorial, which is really 1 times 2 times 3. So I increase the 1 index to 3, the 2 index to 3, and the 3 to 2 because each of those terms, 1, 2, and 3, has an additional factor in the product. So we're keeping track of the numerator and the denominator, the number of terms in the product. And then when we're ready to figure out what is the numerator divided by the denominator, we're going to step through each one. Now obviously 1 is unimportant because 1 divided by 1 is 1. So we can really start at 2. Okay, so if we're calculating it, there is 1 2 in the numerator and 3 2s in the denominator. So what we really have is, if there's 1 2 in the numerator and 3 2s in the denominator, there's really 0 2s in the numerator and 2 2s in the denominator, just using your cancellation. So if we start with 1 as our value, what is going to be, after we finish processing the 2's, what should be the value of our product? Or our numerator divided by our denominator? 1/4, because we are doing 2 divided by 2 times 2 times 2, 1 times that. Well, when we cross out the 1, 2 in the numerator, we end up with 1 times 1 over 2 times 2. So when we're done, that has become 1/4. So what he's asking you to do once you have the numerator and denominator all set up is you iterate through the 2 vectors. Whichever value is larger, if the denominator is larger, you subtract the numerator from the denominator and divide by that number of values. If it is, the numerator is greater, you subtract the denominator from the numerator and you multiply by that number of factors. So when we get to 5 and 6, let's say that, okay, so we have 1/4 after we have done process 2. When we get to 3, Okay, with 3, there is 1 in the numerator, 1 3 in the numerator, and there is 2 3s in the denominator. So there is 1 3 in the numerator and 2 3s in the denominator. So subtracting 1 from 2 gives us 1. So we're going to divide by 3 once. So now we will have 1/12. Okay? When we get to 4, there is again, with 4, there is 1 4, and there are 2 4s in the denominator. So, I'm sorry, there's only 1 4. 1 4 in the denominator. So when we subtract 1 from 1, it's 0. So they cancel out perfectly. And we're still at 1/12. Then we get to 5. There's 1 5. And there's the denominator has now reached the end. So it's by default 0. So there's nothing in the denominator. There's 1 in the numerator. So we're going to multiply now 5/12 by 5 to get 5/12. And finally we get to 6, and again there's 1 6 in the numerator and nothing in the denominator. So again we're going to multiply by a single 6 to get 30/12. So that's what he's trying to get you to do. You can't calculate these binomial coefficients by simply multiplying it out simply 1 times 2 times 3 times 4 times 5, you'll get overflow. So you have to be clever about how you do it, and he's keeping the factors in the numerator and the factors in the denominator in 2 different vectors. And then when he's ready to calculate the fraction, and it's going to generally be a fraction below 1 because your chances of winning a bet are less than 1, you will be dividing like terms and doing cancellation. So that's what he wants you to do. Now the TAs will go over this again tomorrow in the lab, but I wanted to go over it with you, give some intuition for how binomial coefficients are calculated, and what he's trying to get you to do and why, because we don't want overflow. Any questions? I know this is a little bit much. Hopefully you took some notes. Hopefully the TAs going over it again tomorrow will help. We good? Okay. So the next thing we're moving to is BigO notation. And I'm only going to hit BigO notation very quickly today. So BigO notation gives us the approximate running time of an algorithm. Gives us the approximate running time of an algorithm as a function of the size of the input, because the size of the input is important. Okay, if you try to do a linear search of a 10-element array, that is very fast. If you try to do a linear search of a 1 billion element array, that is very slow. So the size of the input is important. Okay? And what we're really counting is roughly the number of instructions. So it really equates to roughly the number of instructions that get executed. So the running time is really roughly the number of instructions that get executed. And on the last day of class in April, we'll talk about how we count the number of instructions. Today, we're just worried in general about introducing BigO notation so that you know what I mean when I write BigO of something. So you will see me write something like BigO of n squared. That means that the running time of the algorithm is roughly n squared instructions, where n is the size of the input. Okay? So for example, if the input is 10 items, then roughly 100 instructions will execute. If there are 1,000 inputs, then that's roughly 1 million instructions that execute. And you typically only see one factor in the big O. And that is because we only care about the largest term. Okay, if we have something like, let's say the running time, which I denote as t of n for the time, this is meant to be the time. Let's say that it's n squared plus 500n plus a million. Okay, well that million looks pretty big, and so does the 500. But as n approaches infinity, what is the only term that matters? N squared. As n approaches infinity, n squared will easily eclipse 500n and 1 million. As big as 1 million looks, it's certainly big. For n equals 10, the dominant term is a million. Okay, for n equals 1,000, n squared is a million, but the dominant term for n equals 1,000 is what? Which is the biggest of those three terms? You can do the math. What is the biggest of these three terms, n squared, 500n, and a million? For n equals 1,000, which is the biggest term? N squared or 1 million, either one. But for n equals 1 million, easily the biggest term is n squared. So all we care about when we look at big O is the biggest term as n approaches infinity. So for big O, we only care about the biggest term. Because in general, the biggest term is going to dominate. Now sometimes it may be for small inputs we do care about the other terms, but in general we're only going to care about the biggest term as n goes to infinity. And we're also going to get rid of constants on the factor. So if we had 3 there, we wouldn't care. Even if it was 1/8, we wouldn't care. Because eventually that constant also gets overwhelmed. So if our function, let's say, was t of n equals sum a n squared plus b n plus c, we say the running time is order n squared, because n squared is the biggest term and we don't care about the constant. Okay? So again, big O is roughly the number of instructions that will be executed given an input of size n, and we only care about the biggest term. Also, we have not yet shown you how to calculate t of n, which is the function that gives the running time or the number of instructions to be executed. We'll consider that on the last day of class. Okay, I just want you to be familiar right now with what big O means. And the book has some good stuff, but the big thing is looking at the running time. So actually constant time is the best. If something runs like an array access where you can get to an element of an array in constant time, we say it's big O of 1, and that means constant time. Okay? Array accesses. For arrays, the average time to find, insert, and delete is order 1. It's constant time. The next best we can do is log n. Okay? Because log n knocks things down a lot. And logs are always to the base 2, not to the base 10. So you've got, in computer science, we leave off the base, but the base is base 2, not base 10. Okay, because everything is binary with us. So you can see that as n gets much bigger, up to 100,000 with log n, when the input size goes up by a factor of 10,000, for log n, the running time increases by a factor of 5. That's outstanding. So here, from 10 to 100,000 is an increase of a factor of 10,000. You can see that the running time of log n increases by only a factor of 5. Okay? For linear time, it increases. So here, it increases by a factor of 5. Here, it increases by a factor of 10,000. It goes from 10 microseconds to 1 second. This is called log linear. Okay, it doesn't increase all that fast because log n doesn't increase all that fast. Okay, now that you know that for log n it goes up by a factor of 5, and for n it goes up by a factor of 10,000, what do you think n log n goes up by a factor of? Well, 50,000, because the log increases by a factor of 5, the linear increases by a factor of 10,000, so log linear is going to be about 50,000 times longer. So it's not horribly worse than linear, but it's not all that much better either. N squared will go up by 10,000 squared, which is, as you can see, from 0.1 millisecond to 2.7 hours. N cubed goes up by a factor of 10,000 cubed, so you go from about 1 millisecond to 31 years. And 2 to the n, which is exponential, is horrific. You can't even, for n equals 50, you're already up to 36 years. And here, these numbers aren't even, the number of atoms in the universe is smaller than 2 to the 100th power. It doesn't matter how fast your computer is, you're really not going to solve this anytime soon. So we are always striving to find algorithms that run as quickly as possible. So the smaller the factor, the better. We prefer constant time to log n to n, and so on and so forth. And there are problems that are called NP-complete. You will get to it in 302. Stands for non-polynomial. It's conjectured that those problems do not have polynomial running times. That the best you can do is exponential. A classic example is the traveling salesman problem. If I tell you that a traveling salesman needs to go to 50 cities, visit each city once, and I want that traveling salesman to travel the minimum possible number of miles, the best known solution takes 2 to the n time to figure out what is the best route for that traveling salesman. That may seem pretty remarkable, but it is true. We know of no polynomial time algorithm that will find the most efficient route for that traveling salesman. And it is conjectured that that problem, the traveling salesman problem, cannot be solved in less than exponential time, but no one has proved it. It's probably the biggest outstanding problem in computer science. It's been worked on for years by both mathematicians and computer scientists, trying to find a proof as to whether the problem is called, does P equal NP? Which is the set of problems that currently are not known, is the set of problems currently for which there is no polynomial solution known Okay, is the set of problems for which there's no polynomial solution, do they have a polynomial solution? And the conjecture is no. And there are ways to proof techniques that reduce a problem to one of the problems in this set. And if you can reduce a problem in this set to your problem, it then belongs to that set. And again, we don't care about it in this course, but the important thing to know is that those problems in NP currently have no better than an exponential time solution. And there are many practical problems. Okay? Actually, cryptography, factoring prime numbers somewhat depends on being able to factor a prime number not being computationally simple. Okay, and then the book gives some graphs that show how these things grow for number of elements, the number of computations you might have to do. So for example, for constant time, you always do 1. For order log n, it increases very slowly. For n, it's linear, so for input of size 6, it takes 6 computations. For 10 elements, it takes 10 computations. If we get to n squared, now for 10 elements, it's 100. And you can see how much bigger it is than order n, and log and constant time are blips. Okay, if we go up to order 2 to the n, order 2 to the n dominates everything. Now only n squared is even coming up here. The other things are flat because of how big order 2 to the n is. So it's just showing you that the graphs for anything bigger than n log n is going to be pretty bad. Okay, so we're always trying to find something better than n log n or better. N squared is generally too much, although there are plenty of algorithms for which we have no better solution than n squared. Okay, matrix multiplication is actually an n cubed one. Just doing a matrix product like you were doing in Lab 5 for a row and a column, that's n squared because it was n rows and n columns. Okay? So are we good with BigO notation? Because I'm going to actually use it almost immediately. Okay. So, moving on. I said I was going to finish up lists. I am going to let you find, there was another solution to the diamond hunter problem, which I'm not really going to go into, but which involved doing a substring find. So last time we showed you how you could do it with lists. You could also have done the finding of the diamonds using a find where you said substring, or actually you said dot find, and you were trying to find a diamond. Okay? And then if you found it, you would delete the diamond from the string, which you can do with strings. In fact, Dr. Planck has a, whoops. He did that where he did a find of a diamond. If he didn't find the diamond, he returned the number of diamonds. If he found the diamond, he incremented the number of diamonds. And then what he did was he concatenated two substrings, the substring up to the diamond and the substring after the diamond. That's what this did, is concatenate the substring before the diamond with the substring after the diamond. Okay? The problem with this approach is that find takes order n time. If n is the size of the string, it takes order n time to find a diamond. And it also takes order n time to get this string, this new string. Okay, because essentially you're taking all but n minus 2 characters from the string. Okay, so in the worst case, there are roughly n diamonds in the mine. If it is, the string is like this, there is roughly n divided by 2 diamonds in that mine, which means that you would repeat the order n operation roughly n divided by 2 times, which gives you order n squared running time. Whereas his algorithm with lists only took order n time, which is why you wanted to use lists rather than this approach with find. So if you would sit down and analyze the running times of each of the two algorithms, the one I presented you last time with a list where you would just delete 2 list elements, that was only order n. And the reason it was only order n is because the find with the list took constant time. Okay, if you were right here at a list, then you were right where you needed to start looking for the next diamond. It essentially was an order 1 operation. And the delete, you were again right there. You were right where you needed to be to do the delete, and you just deleted 2 items. So it turns out the list approach was order n. The approach that would try to use find was order n squared. So it was more efficient to use the list. Now just wrapping up on lists, Qs and DQs, just want to emphasize that when you use each of them. So if you are only accessing the items from the back of a something, so it says if you are simply accessing n elements, okay, so this is use a vector when you only add or subtract from the end. So you use a vector when you add and subtract only from the end. You use a double-ended Q if you add or subtract only from the front or end. And does anyone remember what that type of queue resembles in real life? A line. So a grocery line, a bank line, any kind of line you typically remove from the front and add to the back. And then if you need to insert and delete elements from the middle, you typically would use a list. Okay? So questions about that? Okay. So moving on, we have today's subject, which is sets and maps. So remember that the theme of this course, one of the themes is we want to be able to insert, delete, and find elements in a dynamically changing set. We've already looked at a couple things you could do. You could use an array or a list, or you could use a hash table. Okay, and for a hash table we have average case and worst case. So an array and a list are the worst possible things. A find is order n times for, actually, let's do them separately. Let's have an array. Let's have a list. Whoops. So for an array, the time to find is bad. It's order n. You have to potentially search the entire array for a dynamic collection. Okay, although if it's ordered, you could do it if you was ordered, what would the running time be if you use binary search? It's log n if you use binary search, because you look at only log n elements. For a list, you have to look at every element. You can't use binary search on a list because the elements aren't contiguous in memory the way they are for an array. For a hash table, what was the find? Did you have to search the entire hash table? No. How many buckets in a hash table do you have to search with separate chaining? One bucket, and normally if you've chosen the load factor to be 1, what is the expected number of elements in the bucket? 1. So average case, it is 1. What's the worst case for a hash table? Order n. If every single key hashes to the same bucket, it's order n. So that's the worst case. So insert for an array, we just got through with that. How long does it take to insert into an array? Potentially, if you insert near the beginning. What do you have to do before you actually insert the item? Let's say you know that I'm inserting at position 3 and it's a 10,000 element array. You have to do what? You have to move all 10,000 items, which makes it order n, because you have to move all n items potentially. With a list, what did we say the insertion took? Do you have to look at, if you are right at the item that has to be deleted, do you have to look at all n other items? No. Just one. So it's order 1. Okay, and for a hash table, what was it? Well, again, how many buckets do you have to look at for separate chaining? Get 1. And what do you think the number of average items is supposed to be? 1. So you aren't going to really have to look very far, so it should be order 1. In the worst case, it's order n because there are n items in the, if in the worst case, all n keys will hash to the same bucket. But that would be very rare. Okay, for an array, if I delete the first item of an array, what do I have to do after I delete the first item? Shift all the items to the left. How many items in the array? N. So it takes n move operations, so it's order n. For a list, if I delete, and I'm right at the item that has to be deleted, I just delete that one item. And for a hash table, if I delete, how many buckets do I look at? 1. And we expect only one item to be there, so it's roughly order 1. This is true even with linear probing. With linear probing or double hashing or quadratic probing, we may have to look at more than one entry, but on average, we look at only a constant number of buckets, even for open addressing schemes. And in the worst case, where there's a horrible hashing function, it's order n. Okay, so it seems like we already have a rather good search structure. Of these 3 search structures, which seems to be the best on average? Hash table by a long shot. All 3 of its operations tend to be constant time. So why would we even think about trying to find other ways to organize our data? Well, what happens if I frequently need, I used to be a runner, a competitive runner. I was pretty good. I was one of the best in Knoxville. So I used to care about who was running faster than me. So if I was running a 10K, say, in 17 minutes, or not a 10K, that'd be a world record, by about 9 minutes, actually. If I was running a 5K in 17 minutes, I might like to know what are the set of runners who have finished in less than 17 minutes. Who do I need to get better than? A hash table can't answer this query very efficiently. Why not? What's the key thing that I need in order to answer a query that is to find all people who are less than 17 minutes? Pardon? I don't know their times, right? So I really can't find them in the hash table because I don't know their times. I know they're amorphously less than 17 minutes, but I don't know what their times were. Okay? Now I can do it by looking through the entire hash table, but now I'm down to order n. But let's say I had a list and everything was sorted in the list or in the array. Would that make things simpler if they were all sorted? Yeah, because now they're all going to be next to one another. So what if I could have a data structure that kept things in sorted order, but did better than an array or list for insert and delete? Okay? So we call this type of query, we call it a range query. Because it's asking for all items in a range. Okay, so it's asking for all items in a range. So far, we have dealt only with things called point queries. Okay, so far we've dealt only with what is called a point query. It asks for a single value. It's an equality. So the difference is a point query is an equality, whereas a range query is an inequality. It's asking for all elements A between our key and B. So it wants all keys between A and B. It wants them in a range. Okay? Turns out hash tables are no good on range queries. And maybe sometimes we also need to occasionally print things out in sorted order. Again, hash tables aren't really good for that because they don't keep things in sorted order. The point with a hash table is to randomize it. So we are going to introduce a new data structure, and that is called a set and a map. Okay, so sets and maps, which we'll put over here, their insert time is going to be order log n. Their delete time is going to be order log n. Their find time is going to be order log n. So they're not going to be as good as hash tables at inserting, deleting, and finding. Now, some of the things we look at, their worst case will actually also be log n, whereas for a hash table, the worst case is order n. But in practice, unless you've really messed up, hash tables don't have order n performance. They have constant time performance. So sets and maps aren't going to do as well as hash tables in general. They will take a little longer. But sets and maps will keep their keys in sorted order, which means that we can efficiently do range queries on them. And quickly, once we've found A, then we can iterate through the collection, and the items will all be next to each other. So we can say basically, while then the key is less than B, just keep iterating and printing out those keys. So sets and maps are going to keep their elements in sorted order. But unlike an array, with an array, if I wanted to keep it in sorted order, it required order n time to do an insert. With a set or a map, it's only going to take log n time to do an insert or a delete. Okay, and I'll give you a sneak preview of why. What happens is that sets and maps use something called a tree. We won't get to trees for a couple weeks, but essentially what a tree looks like, let's say I start with the key 100. I put it at what is called the root of the tree. Then I insert 50. 50 is less than 100, so I put it to the left of 100. Now let's say I insert 75. 75 is less than 100, but it's greater than 50, so it goes right here. Now I insert 150, it's greater than 100, it goes over here. Now I insert 175, it's greater than 100 and greater than 150, it goes over here. Now I insert 125, it's greater than 100, less than 150, it goes over here. So essentially what a tree is something that has two children. It's like your family trees, except family trees can have more than two children. So you're allowed, each node can have two children, and what you're hoping for is that it's somewhat balanced. So it's a little like binary search in that it tries to put half the elements to the left of 100 and the other half of the elements to the right of 100. And if it can roughly do that at each node, if at each node roughly half of your children are in your left tree and half of your children in your right tree, then on average you have only log n levels. And I'm not going to go through that now, I'm just giving you a taste of what it's going to be like. Yes?
What happened if you got two 100s? Like you tried to put another 100 in there?
So then you'll see that we have things called multi-sets and multi-maps. In this case, what you would do is just arbitrarily put the 100 either in the left subtree or the right subtree, but you have to be consistent. Okay, you always have to put it. You can't just randomly say one time I'll put in the left tree and the other time I'll put in the right tree. You have to be consistent. But that's what you would do. That, or you do what you do in separate chaining, which is you would just have each node have a list, which also works. Okay, so that's roughly what the data structure we will use, but you don't have to worry about that for the time being. That's just giving you a sneak preview, but it will keep the items in sorted order in some way, which we will get to again when we get to how we implement trees. Okay, for the time being, all you have to know is that sets and maps keep things in sorted order, and that these are the running times of the three primary operations. Now, what's the difference between a set and a map? A set only stores keys. A set stores keys. A map stores key value pairs. Typically, you want a value to be associated with a key. However, sometimes all you care about is the key itself. Let's say that it's voting day and every person is allowed one vote. Okay? So before I'm allowed to vote, I want to see whether I'm the person at the voting booth. Has Brad already voted? And I could use a set for that because all I need is to store the keys of people who have already voted. Whereas normally you want to store key value pairs. In Lab 5, you wanted to store a key, which was the name of your bit matrix, and the value was a pointer to your bit matrix. And this gentleman asked, what happens if I have duplicates? Sets and maps can't store duplicates. If you want to store duplicates, you need a multiset. Stores duplicate keys. So multisets and multi-maps can store duplicate keys. Now, with a multi-map, it's probably not going to be a duplicate key value pair. Most likely, the values will be different, but the keys might be the same. Think of last names. Okay? There might be two people with the same last name, Smith, but very often they'd have different first names. Although on some occasions, two people that are named Smith also have the same first name. But my point is, with a multi-map, it's not duplicate key value pairs. Normally the duplicate is just the key, and the two values are different. Okay? So on Thursday, we're going to pick up with some examples of how to use sets and sets and maps and multi-sets and multi-maps. And we'll also show you the APIs for sets and maps for the standard template library.